I'm Diego from Imagine Optic, and I will introduce our latest metrology system for optical components characterization. So, a brief introduction of Imagine Optic. We are a French company based at the south of Paris with between 60 and 70 people, and some offices in China, in United States, and in Bordeaux. We have also some distributors all around the world. And we are quite proud of two figures. So we have delivered now more than 2,500 wavefront sensors and more than 100 deformable mirrors for high-power lasers. So Imagine Optic is doing as two business units, sensing with the wavefront sensor from hard X-rays to short infrared and some metrology system for optical characterization, live M-squared measurements. And once you measure the wavefront, the quality of the optical system, you can correct those optical aberrations thanks to adaptive optics. So that's the second business unit on the right of my slide with different kind of deformable mirrors and adaptive optics solutions for telescope, for example. Today, I will talk about this metrology system, so MESO, which is designed for production environment and metrology labs. So with this system, you do not need to be optical engineer to measure the wavefront with a nanometer accuracy. And the idea of this system is to build a interferometer-like wavefront sensor, so close to the use of the very known ZIGO and FISO interferometers. And MESO can be complementary because it's keeping the advantage of the wavefront sensor, so it is insensitive to vibrations because we need one single frame to get the wavefront measurement. It can embed up to 4 sources, so different wavelengths. So in this new short infrared version, you can go from 1 micron to 1.7 micron with 4 different sources. For sure, there is an optical zoom in order to keep the high resolution regardless of the size of your sample. And we also integrate a new technology that we call POP for parallel optics procedure, where the idea is to measure parallel optics that are in general thin. And with an interferometer, you get a reflection from the back surface. So you can't measure really the surface flatness, the surface accuracy. And with this new procedure POP, you can measure both surfaces and the transmission of your optics without any preparation. So there is 3 types of procedure in the MESO system. The one I've just mentioned for parallel optics, and then the 2 standard ones, transmission wavefront and surface flatness measurement, thanks to reflected wavefront measurement. You can measure different kinds of optical components. There is a list on the right of my slide. And now I will go on some example and some study cases to show some measurement. So first, an example about how you can measure parallel optics, mirrors, windows, substrate, or disk of any kind of materials by adapting the wavelength. So here it is an R&D team that was studying a new type of infrared material, and they were trying to get the refractive index inhomogeneity map. So to do so, we measure both surface flatness and the transmitted wavefront. And by combining the 3 maps, we can get the refractive index inhomogeneity map. So on the top right, you can see the sample. And then bottom left, the setup. And in the middle, it's the wavefront measurement coming from the MESO. We have an export feature in order to get a file compatible with MetroPro software, which is the most common wavefront analysis software. And that's it. Then MESO can be interesting also for nonlinear crystals and laser crystals after coating. Sometimes you are not able to measure with standard wavelength of this kind of FISO interferometers. So here we measure the small cubic KTP crystals, 9 millimeter square cube, sorry. The wavelength is 1064 nanometer. We can control the polarization if needed, so linear vertical, circular, linear horizontal if needed. And for French laser crystal manufacturer, we developed an add-on on our software in order to measure in one single measurement a batch of different crystals. So you can see in the middle the raw camera signal of the measurement. You can see or guess 4 crystals, cubic crystals. And in one single procedure, then you can have access to 4 different wavefronts for the 4 different crystals. So you can measure a high number of crystals with just one measurement. Another example with some windows. In this case, it was for automotive. So you have a non-transparent windshield glazing that has been measured at 950 nanometer wavelength. And on the bottom left, you can see the raw measurement that require a high dynamic, more than 20 microns root mean square of aberration, deformation. So it's the wavefront distortion. And then you can use the mask editor of the software in order to have a measurement on an area of interest. Here it was a rectangle of 150 millimeter by 70 millimeter between the 2 electrodes that we can see on the right. Well, we can see that with the mask, the quality is better, less than 3 micron root mean square of wavefront error, but still some deformations that can be useful for simulations or to get some idea of the imaging performance of those kind of integrated optics in automotive. And finally, another example about optical system, beam expanders, and how to characterize external beams. So here we tested the MESO in front, we put the MESO in front of a wide LiDAR systems that is supposed to have a very collimated beam. Currently, wavefront is not used to qualify these machines at the end of the production, but it is possible. The most common wavelength is 1550 nanometer. And we measured so this external beam, and at the end you get an independent measurement of the intensity on the right. But what is interesting is the wavefront on the left, the phase of the light wave. And we can then apply some model reconstruction, Zernike, and you can see some different coefficients that can be linked to real-world optical aberration. For example, comma is linked to decentering in the optical system, and spherical aberration, the 8th coefficient, is linked to the design of the lens, so you can do anything with the alignment, but for example, for comma, you can improve the quality of this external beam. It can be useful for guide star lasers or optical telecommunications terminals. That's the idea. Here's a reminder of the features of the MESO and how it can be complementary to your current instrument in the metrology labs, insensitive to vibrations, for embedded wavelengths, and this procedure for parallel optics. Thank you very much.